In a world just overflowing with information, like every single day, there's this flood of articles, papers, data.
It's a lot, a deluge, really.
Yeah, exactly. How do you, quickly get really informed on something complex without just drowning? It feels like a constant challenge.
It absolutely is. And that's really what this deep dive is all about.
Okay.
Think of it as, your personal shortcut to getting it. We try to cut through the noise, pull out the really important bits from the raw material for you.
Great. So today we're digging into this new paper. It's from the International Conference on Machine Learning 2025, the Diffusion Duality. Sounds intriguing.
It is. It talks about this connection, a really remarkable one, between two major kinds of AI models.
And this could potentially change how we build AI for things like text, right? That's the
No,
whole...
that's the promise, yeah.
Yeah.
Our source is, well, it's a dense paper, but fascinating. It's on RCIF 25s or 6.10892 if you want the specifics. But don't worry, our job today is to unpack it. What is this diffusion duality? Why is it such a big deal? And crucially, how does it lead to AI models that aren't just faster, but maybe, smarter, more capable?
Okay, sounds good. Prepare for some aha moments, maybe.
Hopefully. Let's dive in.
All right, so diffusion models. Let's start there. High level, what are we talking about? Powerful generative models inspired by physics.
Exactly. Think about dropping ink into water. It spreads out, gets noisy, right? Diffusion models kind of do that in reverse. They learn to take noise and gradually refine it back into structured data like an image or text. It's about adding noise, then learning to remove it.
Okay, got it. But you said there are two main types.
That's right. So first up, you have Gaussian diffusion models. These are probably the ones you've heard most about.
One's making those amazing AI images.
Precisely. Stunning images. Realistic audio, smooth video, anything with continuous values. These are really well studied. There's a ton of advanced techniques for training them efficiently, making them generate samples super fast, even in a single step sometimes. Lots of innovation there.
Okay, so they're the established stars for continuous data. What's the other type?
The other side is discrete diffusion models.
Yeah.
These are designed for data made of separate, distinct units.
Like words in a sentence.
Exactly.
Yeah.
Text or nodes in a graph, atoms in a molecule, discrete stuff. Now, these are powerful too, but historically, they've been a bit. Well, the paper calls their design space primitive.
Primitive, how so?
They often rely on slower methods like ancestral sampling. It's like generating a sentence, one word, or even one character at a time, step by step. And often once you've put a word down, you can't easily change it later. It can take thousands of these tiny steps.
Wow, okay. That sounds slow and maybe prone to errors you can't fix easily.
That's a key issue, especially with models called masked discrete diffusion models, or MDMs. The paper points out they can struggle badly when you try to speed them up in the few-step regime.
Right.
And they lack this important implicit property, which is something that helps Gaussian models get distilled, made smaller and faster really effectively. Plus, like you hinted, with MDMs, once a token, say a word, is unmasked or generated, it remains fixed.
So if it makes a mistake early on, like generating the cat chase the algorithm, it's stuck with algorithm.
Pretty much. That kind of inflexibility can lead to, well, incoherent results, especially if you're trying to generate quickly. It's like writing in permanent marker.
Yikes. Okay, so that's a problem. Is there an alternative in the discrete world?
There is. There's another type called uniform state diffusion models, or USDMs. These are interesting because they do allow token updates during reverse sampling.
Ah, so they can go back and fix mistakes.
Exactly. They can naturally correct earlier mistakes, which is a huge theoretical advantage over MDMs, self-correction.
I sense a but coming.
Well, yeah. The but is that historically, these USDMs just haven't performed as well as the MDMs in practice. They've kind of underperformed.
Okay, so the flexible ones weren't as good and the good ones weren't flexible. That's the dilemma.
Precisely. Which leads to the big question the researchers tackled. Can we make these flexible USDMs actually competitive? And could that flexibility be the key to finally getting really fast generation for discrete data?
And this is where the duality comes in.
This is where it gets really interesting, yeah. The paper reveals this very remarkable property. They call it the diffusion duality.
Okay.
And what it says, fundamentally, is that a discrete diffusion process, like the one in USDMs, is actually an emergent phenomenon of an underlying continuous Gaussian diffusion process.
Oh, hold on. So the discrete process emerges from the continuous one. They're connected.
Deeply connected. It's like finding out that, I don't know, reggae and classical music somehow share the exact same hidden mathematical structure.
Yeah.
It's a profound link.
How are they connected? What's the bridge?
The bridge is something called the argmax operator.
Argmax.
Yeah.
Sounds technical.
It is a bit, but the idea is simple. Imagine you have those continuous Gaussian latent variables. Think of them as smooth, hidden representations, like a spectrum.
Okay.
Argmax is basically a mathematical way to pick the highest or most likely point in that continuous space and map it to a specific discrete category, like choosing the most likely word. It transforms the continuous distributions into discrete ones.
So it's like a translator between the continuous world and the discrete world.
That's a great way to put it, a translator or a bridge. And discovering this bridge, this duality, has huge implications.
Like what? What does this connection let us do?
Well, it means we can transfer advanced training and inference techniques from Gaussian diffusion to discrete diffusion models. All those clever tricks that made Gaussian models for images so good.
Yeah.
We can potentially borrow them and apply them to discrete models like USDMs. It opens up a whole new design space that just wasn't really accessible before, especially not for those rigid MDMs.
Okay, that sounds powerful. Borrowing the best ideas from the continuous side.
Exactly. Now, it's important to note they are still technically separate Markov chains. They follow their own paths.
Right.
But there's a fascinating theoretical detail. The paper proves, in Theorem 3.1, that the way the discrete model measures how well it fits the data using something called the ELBO, the evidence lower bound actually results in a tighter bound on the likelihood than Gaussian diffusion.
Tighter bound, meaning it's a potentially better or more accurate representation.
Potentially, yeah. It suggests that the discrete view, built on this foundation, might actually capture the essence of the data even more precisely than the underlying continuous one it emerged from. It's like the discrete map is surprisingly more accurate in some ways.
Wow. Okay, that's a cool theoretical wrinkle. So theory is great, but did they build something with this? Did they answer that question about making USDMs competitive?
They absolutely did. They didn't just stop at the theory. They introduced Duo. Duo. It's a framework built squarely on this diffusion duality. And its goals are pretty clear. 1, create a system for discrete diffusion that lets you use all those great Gaussian techniques. And 2, specifically, create language models that support few-step generation, fast generation.
Right, Duo. Built on the duality, what did it achieve? What are the impacts?
The impacts are pretty significant, falling into roughly 3 areas. First, faster training. We're talking a 2x speed up.
Okay, twice as fast to train the model. How?
Duo uses efficient training strategies, and a key one is this low variance curriculum.
A variance curriculum. Sounds smart, like teaching it gradually.
Sort of, yeah. It leverages the underlying Gaussian structure using something called a tempered softmax, which is like a softer version of that argmax translator we talked about.
Okay.
This approach smooths out the learning process and, crucially, drastically lowers the gradient variance. The paper says by an order of magnitude.
An order of magnitude. So like 10 times less variance.
Yeah, something like that. Think of it as trying to learn on a really stable platform instead of a shaky one. Much easier, much faster.
And that leads to the 2x speed up.
Exactly. They show Duo reaching a target performance level, a perplexity score of 35.2 in just 510,000 training steps.
Right.
Which is almost 1.5 points better than another model, UDLM, achieved after 1 million steps. So faster convergence and even slightly better results in half the time.
Half the training time is huge for development. Okay, that's impact 1. What's 2?
Impact 2 is even more dramatic. Faster sampling, like 100x faster generation.
Whoa, okay. 2 orders of magnitude from what baseline?
Well, remember how traditional discrete models, especially older ones, might need hundreds or even thousands of steps? The paper mentions 124 steps as a typical baseline.
Yeah, that's super slow if you want an answer quickly.
Right. So Duo tackles this using a technique adapted from Gaussian models called consistency distillation. They call their version discrete consistency distillation, or DCD.
Consistency distillation.
Yeah.
Making the model's predictions consistent across different noise levels, right? But for discrete data.
Precisely. It lets them condense many, many generation steps into just a few. The result: they reduce the number of steps, or NFEs, function evaluations.
Right, the compute steps.
From that 1024 baseline down to just 8.
8 steps from over 1,000 with minimal quality loss.
Minimal effect on sample quality, according to the paper. They showed the distilled Duo matching the original's quality in 16 steps, and using another trick, a greedy tail sampler, they get it down to 8 steps, sometimes even with slightly better quality metrics.
That's incredible. From thousands of steps to single digits. That changes everything for real-time applications. Okay, training is 2x faster, generation is 100x faster. What's the third impact?
The third is overall improved performance and capabilities, especially thanks to that USDM self-correction ability.
Ah, right, the ability to fix earlier mistakes. How does that play out?
It's crucial. Remember, those MDMs generate tokens, often independently, and can't revise them. This leads to incoherence at low NFEs, basically, gibberish if you try to make them go fast.
Makes sense.
But Duo, being based on USDMs, can self-correct, so it performs much better when you need results quickly in that low NFE regime. On standard tests like LM1B and Open Web Text, Duo beats previous USDMs and Gaussian models. And critically, it outperformed MDMs, especially when speed matters.
Okay, better than other diffusion models. How about compared to, say, standard autoregressive models like GPT?
That's interesting too. In zero-shot evaluation testing on tasks, it wasn't specifically trained for Duo, actually surpasses AR models on 3 out of 7 zero-shot datasets they tested.
Wow, so it's not just catching up, it's actually beating established architectures on some tasks out of the box.
It suggests Duo is not just fast, but also robust and capable, a really strong combination.
Okay, this is really compelling stuff. So stepping back for you listening, this deep dive really shows how fundamental research, like finding this duality, can unlock massive practical improvements.
Absolutely. It's not just tweaking things a little bit. This is a foundational shift.
And the practical implications. I mean, think about AI dealing with text.
Yeah. Much faster, more accurate chatbots, summarization tools, maybe even code generation assistance. The list goes on.
And it's not just text, is it? You mentioned molecules, graph.
Exactly. Drug discovery, materials science, analyzing complex networks. Anywhere discrete data is key, these faster self-correcting models could have a huge impact.
And beyond the applications, there's just, I find the core idea really elegant. This notion that discrete structures can kind of emerge from a continuous background.
It is elegant. It's a beautiful piece of science, finding these deep connections between seemingly different mathematical worlds within AI. It reminds us how interconnected these ideas can be.
So let's recap quickly. We've explored the diffusion duality.
This bridge between continuous Gaussian models and discrete uniform state models, enabled by that argmax idea.
And it's not just theory. It's a practical engine, powering the Duo framework.
Leading to real breakthroughs, 2x faster training.
And that incredible 100x faster sampling, going from thousands of steps down to maybe 8.
While also boosting performance and allowing that crucial self-correction that other discrete models lacked.
It really paints a picture of how connected, continuous, and discrete data representations can be inside these powerful AI models.
Which brings us to a final thought for you to ponder. The paper proves that the discrete model's way of fitting the data, its ELBO, is actually tighter than the underlying Gaussian one.
Right, the slightly more accurate map.
So the question is, what might this fundamental tightness, this potentially more precise way the discrete model captures information, even though it emerges from the continuous, what might that imply about the best way to represent information in AI? Does discreteness hold some kind of fundamental advantage for capturing certain truths about data? And how could that insight shape where AI goes next?